Dreamcraft 3D, Hierarchical 3D generation with Bootstrapped Diffusion prior. We present Dreamcraft 3D, a hierarchical 3D content generation method that produces high-fidelity and coherent 3D objects. We tackle the problem by leveraging a 2D reference image to guide the stages of geometry sculpting and texture boosting. A central focus of this work is to address the consistency issue that existing works encounter. To sculpt geometries that render coherently, we perform score distillation sampling via a view-dependent diffusion model. This 3D prior, alongside several training strategies, prioritizes the geometry consistency but compromises the texture fidelity. We further propose bootstrapped score distillation to specifically boost the texture. We train a personalized diffusion model, DreamBooth, on the augmented renderings of the scene, imbuing it with 3D knowledge of the scene being optimized. The score distillation from this 3D-aware diffusion prior provides view-consistent guidance for the scene, notably through an alternating optimization of the diffusion prior and 3D scene representation. We achieve mutually reinforcing improvements. The optimized 3D scene aids in training the scene-specific diffusion model, which offers increasingly view-consistent guidance for 3D optimization. The optimization is thus bootstrapped and leads to substantial texture boosting. With tailored 3D priors throughout the hierarchical generation, Dreamcraft 3D generates coherent 3D objects with photorealistic renderings, advancing the state-of-the-art in 3D content generation. Code available at the project's website. A picture is worth 1,000 words. Principled recaptioning improves image generation. Text-to-image diffusion models achieved a remarkable leap in capabilities over the last few years, enabling high-quality and diverse synthesis of images from a textual prompt. However, even the most advanced models often struggle to precisely follow all of the directions in their prompts. The vast majority of these models are trained on datasets consisting of image-caption pairs, where the images often come from the web, and the captions are their HTML alternate text. A notable example is the Leon dataset, used by Stable Diffusion and other models. In this work, we observe that these captions are often of low quality, and argue that this significantly affects the model's capability to understand nuanced semantics in the textual prompts. We show that by relabeling the corpus with a specialized automatic captioning model and training a text-to-image model on the recaptioned dataset, the model benefits substantially across the board. First, in overall image quality. For example, FID 14.84 versus the baseline of 17.87, and 64.3% improvement in faithful image generation according to human evaluation. Second, in semantic alignment. For example, semantic object accuracy 84.34 versus 78.90, counting alignment errors 1.32 versus 1.44, and positional alignment 62.42 versus 57.60. We analyze various ways to relabel the corpus and provide evidence that this technique, which we call recap, both reduces the train-inference discrepancy and provides the model with more information per example, increasing sample efficiency and allowing the model to better understand the relations between captions and images. An early evaluation of GPT-4V ision. In this paper, we evaluate different abilities of GPT-4V, including visual understanding, language understanding, visual puzzle solving, and understanding of other modalities, such as depth, thermal, video, and audio. To estimate GPT-4V's performance, we manually construct 656 test instances and carefully evaluate the results of GPT-4V. The highlights of our findings are as follows. 1. GPT-4V exhibits impressive performance on English visual-centric benchmarks, but fails to recognize simple Chinese texts in the images. 2. GPT-4V shows inconsistent refusal behavior when answering questions related to sensitive traits such as gender, race, and age. 3. GPT-4 V obtains worse results than GPT-4 API on language understanding tasks, including general language understanding benchmarks and visual common sense knowledge evaluation benchmarks. 4. Few-shot prompting can improve GPT-4V's performance on both visual understanding and language understanding. 5. GPT-4V struggles to find the nuances between two similar images and solve the easy math picture puzzles. 6. GPT-4V shows non-trivial performance on the tasks of similar modalities to image, such as video and thermal. Our experimental results reveal the ability and limitations of GPT-4V, and we hope our paper can provide some insights into the application and research of GPT-4V. CommonCanvas, an open diffusion model trained with Creative Commons images. We assemble a dataset of Creative Commons licensed images, which we use to train a set of open diffusion models that are qualitatively competitive with Stable Diffusion 2. This task presents two challenges. 1. High-resolution images lack the captions necessary to train text-to-image generative models. 2. Images are relatively scarce. In turn, to address these challenges, we use an intuitive transfer learning technique to produce a set of high-quality synthetic captions paired with curated images. We then develop a data and compute-efficient training recipe that requires as little as 3% of the Layer 2B data needed to train existing Stable Diffusion 2 models, but obtains comparable quality. These results indicate that we have a sufficient number of images, approximately 70 million, for training high-quality models. Our training recipe also implements a variety of optimizations that achieve about 3 times training speedups, enabling rapid model iteration. We leverage this recipe to train several high-quality text-to-image models, which we dub the CommonCanvas family. Our largest model achieves comparable performance to Stable Diffusion 2 on a human evaluation, despite being trained on our dataset that is significantly smaller than Layan, and using synthetic captions for training. We release our model's data and code at the project's website. QMoE, practical sub-1-bit compression of trillion-parameter models. Mixture of experts MoE architectures offer a general solution to the high inference costs of large language models, LLMs, via sparse routing, bringing faster and more accurate models at the cost of massive parameter counts. For example, the Switch Transformer C2048 model has 1.6 trillion parameters, requiring 3.2 terabytes of accelerator memory to run efficiently, which makes practical deployment challenging and expensive. In this paper, we present a solution to this memory problem in form of a new compression and execution framework called QMoE. Specifically, QMoE consists of a scalable algorithm which accurately compresses trillion-parameter MoEs to less than 1 bit per parameter, in a custom format co-designed with bespoke GPU decoding kernels to facilitate efficient end-to-end compressed inference, with minor runtime overheads relative to uncompressed execution. Concretely, QMoE can compress the 1.6 trillion parameter Switch Transformer C2048 model to less than 160 GB, 20x compression, 0.8 bits per parameter, at only minor accuracy loss, in less than a day on a single GPU. This enables, for the first time, the execution of a trillion-parameter model on affordable commodity hardware, like a single server with 4x NVIDIA, a 6000 or 8x NVIDIA 3090 GPUs, at less than 5% runtime overhead relative to ideal uncompressed inference. The source code and compressed models are available at project's website. Wonder 3D single image to 3D using cross-domain diffusion. In this work, we introduce Wonder 3D, a novel method for efficiently generating high-fidelity textured meshes from single-view images. Recent methods based on score distillation sampling, SDS, have shown the potential to recover 3D geometry from 2D diffusion priors, but they typically suffer from time-consuming per-shape optimization and inconsistent geometry. In contrast, certain works directly produce 3D information via fast network inferences, but their results are often of low quality and lack geometric details. To holistically improve the quality, consistency, and efficiency of image to 3D tasks, we propose a cross-domain diffusion model that generates multi-view normal maps and the corresponding color images. To ensure consistency, we employ a multi-view cross-domain attention mechanism that facilitates information exchange across views and modalities. Lastly, we introduce a geometry-aware normal fusion algorithm that extracts high-quality surfaces from the multi-view 2D representations. Our extensive evaluations demonstrate that our method achieves high-quality reconstruction results, robust generalization, and reasonably good efficiency compared to prior works. LLM FP4, 4-bit floating-point quantized transformers. We propose LLM FP4 for quantizing both weights and activations in large language models, LLMs, down to 4-bit floating-point values in a post-training manner. Existing post-training quantization PTQ solutions are primarily integer-based and struggle with bit widths below 8 bits. Compared to integer quantization, floating-point quantization is more flexible and can better handle long-tail or bell-shaped distributions, and it has emerged as a default choice in many hardware platforms. One characteristic of floating-point quantization is that its performance largely depends on the choice of exponent bits and clipping range. In this regard, we construct a strong floating-point PTQ baseline by searching for the optimal quantization parameters. Furthermore, we observe a high interchannel variance and low intrachannel variance pattern in activation distributions, which adds activation quantization difficulty. We recognize this pattern to be consistent across a spectrum of transformer models designed for diverse tasks, such as LLMs, BERT, and vision transformer models. To tackle this, we propose per-channel activation quantization and show that these additional scaling factors can be reparameterized as exponential biases of weights, incurring a negligible cost. Our method, for the first time, can quantize both weights and activations in the Llama 13B to only 4-bit and achieves an average score of 63.1 on the common sense zero-shot reasoning tasks, which is only 5.8 lower than the full precision model, significantly outperforming the previous state-of-the-art by 12.7 points. Code is available at the project's website. TD-MPC2, Scalable Robust World Models for Continuous Control. TD-MPC is a model-based reinforcement learning algorithm that performs local trajectory optimization in the latent space of a learned implicit world model. In this work, we present TD-MPC2, a series of improvements upon the TD-MPC algorithm. We demonstrate that TD-MPC2 improves significantly over baselines across 104 online RL tasks, spanning 4 diverse task domains, achieving consistently strong results with a single set of hyperparameters. We further show that agent capabilities increase with model and data size and successfully train a single 317 M-parameter agent to perform 80 tasks across multiple task domains, embodiments, and action spaces. We conclude with an account of lessons, opportunities, and risks associated with large TD-MPC2 agents. Explore videos, models, data, code, and more at the project's website. ConvNets match vision transformers at scale. Many researchers believe that convolutional neural networks perform well on small or moderately sized datasets, but are not competitive with vision transformers when given access to datasets on the web scale. We challenge this belief by evaluating a performant ConvNet architecture pre-trained on JFT4B, a large labeled dataset of images often used for training foundation models. We consider pre-training compute budgets between 0, 4K and 110K TPU v4 core compute hours, and train a series of networks of increasing depth and width from the NFNet model family. We observe a log-log scaling law between held-out loss and compute budget. After fine-tuning on ImageNet, NFNets match the reported performance of vision transformers with comparable compute budgets. Our strongest fine-tuned model achieves a top 1 accuracy of 90.4%, detecting pre-training data from large language models. Although large language models, LLMs, are widely deployed, The data used to train them is rarely disclosed. Given the incredible scale of this data, up to trillions of tokens, it is all but certain that it includes potentially problematic text, such as copyrighted materials, personally identifiable information, and test data for widely reported reference benchmarks. However, we currently have no way to know which data of these types is included, or in what proportions. In this paper, we study the pre-training data detection problem. Given a piece of text and black box access to an LLM without knowing the pre-training data, can we determine if the model was trained on the provided text? To facilitate this study, we introduce a dynamic benchmark, Wikimia, that uses data created before and after model training to support gold truth detection. We also introduce a new detection method, min-k%prob, based on a simple hypothesis. An unseen example is likely to contain a few outlier words with low probabilities under the LLM, while a seen example is less likely to have words with such low probabilities. Min-k%prob can be applied without any knowledge about the pre-training corpus or any additional training, departing from previous detection methods that require training a reference model on data that is similar to the pre-training data. Moreover, our experiments demonstrate that min-k%prob achieves a 7.4% improvement on Wikimia over these previous methods. We apply min-k%prob to two real-world scenarios: copyrighted book detection and contaminated downstream example detection, and find it a consistently effective solution. CLEX, continuous length extrapolation for large language models. Transformer-based large language models, LLMs, are pioneering advances in many natural language processing tasks. However, their exceptional capabilities are restricted within the preset context window of Transformer. Position embedding PE, scaling methods, while effective in extending the context window to a specific length, demonstrate either notable limitations in their extrapolation abilities or sacrificing partial performance within the context window. Length extrapolation methods, although theoretically capable of extending the context window beyond the training sequence length, often underperform in practical long-context applications. To address these challenges, we propose continuous length extrapolation, CLEX, for LLMs. We generalize the PE scaling approaches to model the continuous dynamics by ordinary differential equations over the length scaling factor, thereby overcoming the constraints of current PE scaling methods designed for specific lengths. Moreover, by extending the dynamics to desired context lengths beyond the training sequence length, CLEX facilitates the length extrapolation with impressive performance in practical tasks. We demonstrate that CLEX can be seamlessly incorporated into LLMs equipped with rotary position embedding, such as Llama and GPT-NEOX, with negligible impact on training and inference latency. Experimental results reveal that CLEX can effectively extend the context window to over 4 times or almost 8 times the training length, with no deterioration in performance. Furthermore, when evaluated on the practical long bench benchmark, our model trained on a 4K length exhibits competitive performance against state-of-the-art open-source models trained on context lengths up to 32K. LightSpeed, light and fast neural light fields on mobile devices. Real-time novel view image synthesis on mobile devices is prohibitive due to the limited computational power and storage. Using volumetric rendering methods, such as NeRF and its derivatives, on mobile devices is not suitable due to the high computational cost of volumetric rendering. On the other hand, recent advances in neural light field representations have shown promising real-time view synthesis results on mobile devices. Neural light field methods learn a direct mapping from a ray representation to the pixel color. The current choice of ray representation is either stratified ray sampling or plucker coordinates, overlooking the classic light slab two-plane representation, the preferred representation to interpolate between light field views. In this work, we find that using the light slab representation is an efficient representation for learning a neural light field. More importantly, it is a lower-dimensional ray representation, enabling us to learn the 4D ray space using feature grids, which are significantly faster to train and render. Although mostly designed for frontal views, we show that the light slab representation can be further extended to non-frontal scenes, using a divide-and-conquer strategy. Our method offers superior rendering quality compared to previous light field methods and achieves a significantly improved trade-off between rendering quality and speed. TiC-CLIP, continual training of CLIP models. Keeping large foundation models up to date on latest data is inherently expensive. To avoid the prohibitive costs of constantly retraining, it is imperative to continually train these models. This problem is exacerbated by the lack of any large-scale continual learning benchmarks or baselines. We introduced the first set of web-scale time continual (TIC) benchmarks for training vision language models, TiC DataCompt, TiC YFCC, and TiC RedCaps, with over 12.7 billion time-stamped image-text pairs spanning 9 years, 2014 to 2022. We first use our benchmarks to curate various dynamic evaluations to measure temporal robustness of existing models. We show OpenAI's CLIP, trained on data up to 2020, loses approximately 8% zero-shot accuracy on our curated retrieval task from 2021 to 2022, compared with more recently trained models in OpenCLIP repository. We then study how to efficiently train models on time-continuous data. We demonstrate that a simple rehearsal-based approach that continues training from the last checkpoint and replays old data reduces compute by 2.5 times when compared to the standard practice of retraining from scratch.